in class, if you were here, remember we talked about valence bond theory. We talked about the valence bond theory. So with the valence bond theory, what that is saying is, if you guys remember orbitals, right? We have s, p, d, and f orbitals. So the s orbital would be something like just a sphere, okay, with that being the nucleus, okay? So a sphere. And then the p orbital would be something like a dumbbell, okay? So similar to that. And then the d orbital would be something like 2 p orbitals, okay? That's a bad one. So 2 p orbitals like that. I'll shade it in just to make it not look like I messed up. And then f would be basically the same thing, but with 1 more p orbital. So it would have, if you think of having like axes, okay, and then like this being x and y, and then that's a y, and then z, but z is actually kind of coming out at us and going back into the paper. So there would be a p orbital here along this axis, and then a p orbital here along this axis, and then one here kind of sticking out of the page, and then kind of behind the others. Okay, so sticking behind, so it's kind of like out at us. So that's what we've learned already this school year. I understand you might have forgotten some, so that's why we're reviewing. So that's the valence bond theory has to do with these orbitals overlapping each other to form bonds. So that's what valence bond theory really is. So an example of these bonds overlapping, they can do it by creating a sigma bond, okay, sigma bond. Or they can do it by creating a pi bond, okay? So a pi bond, which would be like the second and third bonds in the double and triple bonds. So what that looks like is, we'll go over some examples, but a sigma bond with orbitals would look, you can have an s to s bond, okay? So s orbital to s orbital bond, and that would just look like this, where these are overlapping, and here are the nuclei, and the orbitals are overlapping, okay? So that is an s to s bond, and then you can have an s to p bond, where you have something like this from the s block, like hydrogen, and then something from the p block, like maybe chlorine or something, and they overlap here. So that would also be a sigma bond. Another way you can have a sigma bond is by maybe 2 things from the p block overlapping, the p orbitals overlapping head to head. So what head to head means, you can consider that like the head of it. So it would look similar to this, like maybe chlorine. Okay, so you would have a p orbital bonding with a p orbital head to head. So now those are the sigma bonds. Those are any single bonds. So for example, you can have like hydrogen bonded with hydrogen. That bond right here is a sigma bond. Okay, with the sp, that would be like hydrogen bonding with a chlorine. Okay, that's an that's an s and a p. Okay, from S block, P block from the periodic table. And then this P to P could be like fluorine bonding with fluorine. Okay, and then they would bond head to head like this. So that's a sigma bond as well. Okay, now pi bonds, a pi bond would look like when 2 p orbitals overlap each other, not head to head, but side to side. So you have side to side overlapping. So that is a pi bond. And don't get confused thinking this is 2 pi bonds. This is 1 pi bond. Okay, so I'm being strict with that or calling your attention to that because later when you see these two involved in a big molecule, you're going to think that maybe that's a double bond when it's not. It's just a single bond. When two pi bonds are overlapping side to side, that's just one pi bond. Now, for the actual point I want to make today, not just valence bond theory. Valence bond theory covers a lot, talking about overlapping of these, but you do need to know the difference between sigma and pi bond. That's more vocabulary. But something like the main focus for today, I want you to look at molecular geometry versus electron pair geometry. So molecular geometry versus electron pair geometry. So in semester 1, we've already learned molecular geometry. We'll go over a few examples. So there's linear, there's tetrahedral, there's bent, trigonal planar, trigonal, bipyramidal, and there's one more. Okay, so we have these 6 types of molecular geometry that we've learned already. So linear could be involved with 2 to 3 atoms, 2 atoms looking like this, or 3 atoms looking like this, okay? And the balls are just atoms. Tetrahedral would be with 5 atoms and 1 central atom bonding with 4 different atoms with no lone pairs in the middle. Bent would be with 3 atoms, and it would look like this. This is your typical water molecule, I guess, if you want to picture it. And this has 2 lone pairs of electrons. Trigonal planar is with 4 atoms, and you have a central atom with no lone pairs, and then 2 atoms sticking off of it here, and then a double bond up here, usually with oxygen, but it could be with sulfur or selenium, depending on what I throw in the test question, but usually it's oxygen. And trigonal bipyramidal, I'm going to do, I guess, right here with, it has 6 atoms, and we'll draw it here. So 6 atoms, and you have a central atom with no lone pairs, and this is the one that breaks the octet rule, okay? And it has 5 bonds off of the central atom. And then pyramid is with 4 atoms, and you have a central atom with 3 atoms bonded on it, and then you have a lone pair. So what's the difference between molecular geometry and the new geometry we learned today? We've always looked at like tiny molecules like these, the up to 6 atom molecules, but here in this test, we're going to be looking at really big molecules. And let me just grab a molecule off of our homework. One molecule from our homework that we will be looking at, so we have this molecule here. This molecule has a certain amount of things that are assumed when you look at it. So assumed are these right here. These corners here are carbon atoms. So assumed those are carbons, 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 and carbon. So what this atom really looks like is carbon, carbon, oxygen, carbon, carbon, and then another carbon here and another carbon here. And what else is assumed when you look at just the purple part up here? What else is assumed are hydrogens and electron pairs. So with the hydrogens, you just look at the carbon. The carbon needs 4 bonds total. So however many bonds it'll need, you're going to add those hydrogens. So for example, carbon here has 1 bond. That means it's going to need 3 hydrogens to complete its octet, okay, to make it stable. So assumed here, when we didn't even have this, assumed was a carbon and 3 hydrogens. So assumed here would be CH3. Assumed here, CH3, okay? Same with here. Assumed here, CH3, CH3, okay? So that means this needs 3 more hydrogens This will actually only need 1 hydrogen because it has 3 bonds and it needs 4. This one, 1, 2, 3, so there is a hydrogen sticking off. And don't think this is flat. That hydrogen's going like backwards, actually almost directly behind carbon. And then this one will have 3 hydrogens sticking off of it. And same with this one. So now we need to look at oxygen. So oxygen over here has 1, 2, 3, 4, 5, 6 valence electrons. Okay, if you look at the periodic table, the trend, it shows that everything in group 6, if you're not looking at the D block, everything in group 6 has 6 valence electrons. So you have something bonded here. Okay, we don't really care. It's an element. Okay, something bonded here with its atom, and then there's some element here, and it's bonded here. So we have this oxygen, that's bonded like that, and so this valence pair will go up here, or lone pair will go up here, and we will actually have 2 pairs of lone pairs of electrons up here. So you draw them here. Okay, so when you see an element like, or a molecule like this without the blues and the reds, there are a lot more things that can be assumed about that molecule. So what we're looking at, electron pair geometry versus molecular, what's the difference? So the difference is with molecular geometry, we're looking at the whole molecule, including these pairs of electrons as a pair of electrons. And we look at them differently than a bond. Well, in electron pair geometry, we don't look at them any different than a bond, because really what they are and what we're looking for in electron pair geometry are areas of electron density, okay? So we're looking at areas of electron density. So if we look at, what color haven't I used? Green. So let's say I ask for the electron pair geometry of this atom alone. And that's really what's mainly different, other than the fact that we look at these as a bond or a electron density. But in this side, when we did it earlier this year, we looked at the whole molecule. Guys, if we were to name every molecule with its own geometry shape, we would have millions of names and it would defeat the purpose, because we might as well just call it its name. So instead of calling this whole molecule a certain shape, we actually look at certain parts of the molecule and then call it its shape. So the good thing is none of the vocabulary is new. Actually some we don't even use. We won't use this one anymore. And pyramid. So basically we look at the ones with lone pairs and they actually will change. So here, if we're looking at the molecular geometry versus the electron pair geometry, okay? So here we would have oxygen with 2 pairs of electrons, and then we don't really care what's sticking off of it. Something is, okay? So that's obviously easy to recognize. It's bent, right? So that would be bent. However, if we were to draw this again, so let's say we're looking at it a different way, okay? We're looking at electron densities, areas of electron densities, and not necessarily looking at these as different things. So basically a bond is electron densities, right? We looked at that up here. So an electron density is where electrons are located, or most likely to be located. So a bond is literally 2 electrons. It's an electron density. So we have an electron density here, right? And we're going to call that the nucleus. That's oxygen, but that's the nucleus of the oxygen. And we have an electron density here. And then we have an electron density here, and then one here. So if you look at it a certain way, or you can just go by the rules, this is no longer bent, but it is tetrahedral. It is a shape like that, if we're only looking at electron densities. We are going to look at how these orbitals here hybridize tomorrow.